These classical CV2 networks are known as shallow networks, and because those are hand engineered, those will not be learning anything other than what you have engineered in your feature extractors. That's it. So it's your choice. Okay, let's move further. Okay, let me tell you what are different data sets available. Now, I hope most of you guys are aware of dataset, what dataset is. This is what your deep neural network will be trained on. Now we are done with classical approaches. Okay, now we'll be deep diving into deep learning approaches, and I will make you aware. I will try whatever I can tell you guys. So let's see what we have. So dataset, what are the different data sets available for you if you guys invent some like new algorithm, and if you want to test on that, what you can do is, so there is one data set available as Pascal VOC. VOC abbreviated as Visual Object Classes. You have COCO dataset as well, which is known as Common Object in Context. And you have ImageNet. Now, ImageNet competition is very famous. Most of you guys might have heard of it. Like AlexNet got famous from there only. Your VGG16 got famous from there only. So they participate in that kind of competition in which they have to like classify 1,000 different objects. They have 2 different data set as well. 200 is also there. So you can see in Pascal VOC, you have 20 different classes. In case of COCO, you have 80 different classes. Now, if you ask me which data set should you use for training your algorithm or your model, it's better not to go with ImageNet dataset, because ImageNet dataset do not have like multiple objects in single image. Now, if you are building any object detection algorithm, you will want that in a frame, if multiple object comes, it should be able to detect them. But ImageNet dataset mostly contains images which have only single objects in them. So it's your choice, but most probably don't go for ImageNet dataset for training of object detection algorithm. After that, you have a choice for Pascal as well as COCO dataset. In COCO dataset, in Pascal dataset, you have 11,000 images. That's a small dataset, I will say, compared to what a COCO dataset, it has 330,000 something images. And in 11,530 images, you can see we have 27,450 reason of interest. Now, reason of interest is image might be having multiple objects inside it. So they might have annotated, or they might have created ground truth around those boxes, around those objects. So in total, 11,530 images, and that you will be getting 27,450 objects to learn from, and 20 different classes. And you have second choice for COCO dataset, which is a bigger data set compared to Pascal, and which will be having 1.5 million object instances inside it. Total, this 330,000 images will be having 1.5 million object instances inside it, and 80 different classes. Now it's your choice what to go for, but I will suggest go for Pascal VOC first. Okay, go for Pascal VOC first. It's a small data set. If your algorithm perform well, then go for COCO data set. And we'll be looking forward for some paper outcomes related to these 2 data sets. We'll not be going for ImageNet because that isn't a data set you should be interested for training your object detection algorithm. Let's move further. Let me give you some examples from this data set. You can see here, right? You can see a Pascal data set, how it looks like. So you have an image and you have the bounding boxes around it. So these are the annotation that they have provided you. You can see, right? The people sitting, they are also, humans are also there. And what else do we have? Children, there is some bottle, I guess. So they have also down bounding box around it. We have chair as well, and they will also be having a label towards it, right? Let's see this COCO data set. So COCO data set is very good to use, go with. If you want to, okay, if you want to explore this thing, COCO dataset, go for their website. It's very good website. You have the option to select what kind of objects you want in the images. Let's say you click on humans and dogs. Let's say here you click on humans and dogs. You will just get the images of human and dog. You can save them. Like you can see here, one human is there. Here one dog is there. Human and again a dog. Human and again a dog. So COCO dataset is well maintained. If you want to go and if you want to have some specific objects into your images, you can have that option there. You might not have that option in this Pascal dataset. That's your choice. When you want to experiment with, you can go for it, or you can take whole dataset as well. Okay, now tell me, now the question comes, what if you want to generate your own data? Like these are all the objects they have in their data set, but what if the object you are searching for isn't here? So what you can do is that will be something known as manual task for you. You have to collect all the images, and you there are some softwares known as softwares like Label MG. So this kind of softwares are there in the market. You can use this kind of softwares, and what you have to do is just you have to build a bounding box around this object, and it will itself find out whatever coordinates or whatever useful information is required for training your model. Just have to label it, whether it is a person, whether it is a cat, whether it is a dog. I guess someone has unmuted themselves. I'll mute them. Okay. So what I was telling you, it might happen that in some of the examples, I request all of you to keep your mic off. Okay. It might happen in some of the cases that whatever object you are having interest in, whatever algorithm you want to build for, that object might not be inside your data set, and you will yourself has to develop that data set. So in that case, you have support of this kind of softwares using which you can have this data set ready, and you can search for this Label MG software as well. Now that I have shown you something regarding this object detection field, you have seen what are the data set available. Two data set what I've told you, that is this COCO data set as well as Pascal data set. Now let's move further and let's deep dive into deep networks. We have seen the data set. Now let's see what are the architectures. This was our previous thing, right? There was an image, we used to extract out the features, then we used to pass it to the classifier, right? SVM, and then we used to have the bounding box. Now let's forget it. Now let's deep dive into deep networks. Now, how many of you are aware of classification task? Just write in the comment section, how many of you are aware of doing classification using convolutional neural networks? Or you might have attended my lecture last time. Okay, I can see yes from Sapna. Aware. So people are aware of it, right? What a classification task, how you can do it. So basically, I will repeat it. What do we have? Gupta is unaware of it. So let me tell you. So I will wrap it quickly. So you have an image of a cat. You have a network which is well trained, already trained on, or you can train them as well. So you have an AlexNet, or you can take another whatever transfer learning you want to do. AlexNet or BGG, you pass that image, you get some feature vectors or say feature maps, you convert them into 1D. After that, you have fully connected layers, and at the end you have a softmax layer which will provide you with the confidences, whether what kind of image that that is which you have passed to the network. So this was the simple classification task. Now what do you want? We want that a box should also be there. How will you create a box around that image? You want a box as well. You just don't want to classify it, right? You want to localize it. How can you do that? So okay, so here comes the bounding box concept. So already what we have an image. We provided it to CNNs. It used to give us some softmax score, and based on that we used to make it belong to certain class. Now what a simple thing you have to do is you have to have 4 different layers. Okay, don't go here, first go here. So how will you create a bounding box? So this kind of bounding boxes you yourself has to create on your data set. Okay, it's not like it will automatically detect it. First of all, you have to train him where the bounding boxes are. So let's say if you have a box here, you can see here we have a box for a cycle, we have a box for a boat as well, right? And how are they labeled? Let's say you have drawn a box here. What you can do is just extract out the x1, y1, x2, y2. You want this labels, okay? You want to create the data set which will be having this labels as well. Now, what the labels? I mean to say the coordinates. So you will be having this x1, y1 and this x2, y2, or you can take it differently. You can give x and y of the center of the box, give the x and y, and give the height and width of the box. So you have to make the architecture learn this thing. You have to tell him, you just don't have to do the classification kind of thing. Parallelly, what you want to do is you want to detect where the box should be and what are the coordinates. Once the algorithms provide you with this coordinates, you yourself can draw the box there. So algorithm is trained to provide you with this coordinates, and using simple CVT tools, you can have the box there. Now, but how will you do that? Earlier, we used to have a single layer, right? We used to have a single layer which used to give us the confidence. Now what you have to do is you just have to stack up 4 more layers parallelly. You can divide the network into 4 different things. Okay, go and study regarding it, but yes, things are there. You can do it like this way also. So what do we have here? So what will this first box belongs to? This will be x1, this will be y1, this will be x2, this will be y2. So you will be training your model parallelly. It will be doing classification, as well as it will be giving you the x1, y1, x2, y2 as well. So while training, you have to have this data. What are the coordinates for the input image which you are giving for training? And that you have to generate using whatever software tool we have seen, like label MG is there. Or if you are going for the data set, they will be having them in the data set. The data will be there. Okay, where are the bounding boxes? So but we are not going inside of those kind of thing, but just let's see how simple way we can do it. For now, we have seen we can do it like this. Okay, but how will the model will get trained? Here we know about loss function, right? But what kind of loss will be here? So you can use here L2 loss. What a L2 loss will be? So let's take an example. Let's say we have an image and we have a boat over here. We have a coordinates that this will be 200 in x-axis. This will be 250. This will be 600, and this will be 400 for y2. What you can do is you just have to train your model. Let's say first of all your expected are 200, 250, 600, and 400 for respect to x1, y1, x2, y2. Now your model is not trained on it, but it is trying to train himself. So first of all, it might predict that it is 0, 0, 800, and 600. But yeah, we know it is wrong. How do you penalize the model? So if you know about classification, you have log loss function there. Here you have the squared loss. Okay, what you can do is you just have to subtract the expected value and whatever is the predicted one, square it for all the 4 coordinates, x1, y1, x2, y2, and sum them all, and you will get an penalty value of this thing, right? You can see the figure. And the next thing, whenever the model gets penalized, it will try to predict it more accurately. And let's say in next step you get 100, 150, 700, and 450. And again you calculate those loss with respect to your expected outcomes, and you will again get the loss reduced. And these are the hypothetical values. So I didn't take it, I didn't scale it, just take it. These are some random values. So yeah, at the end it might happen that your architecture will come close to your expected values and your loss will be 0. So what kind of loss we are using? We are using L2 loss here. So what will be we having? We'll be having a classification, as well as we'll be having this bounding box regressor kind of thing, and which will be having a loss, which is a L2 loss, using which the model will learn what should be where should be my bounding box, what should be the coordinates of whatever thing I have classified. Now, one more specialty about bounding boxes, if you train your architecture like that, let's say you have an image which is like half image of a car. So it will itself detect how much long the car may be. You can see the image is not having the full car inside of it, and the model is telling that it might be 500 in this direction and 300 in this direction. 300 is okay, it is able to find out from that image. But what about the length of the car? So it might have seen it in its training data that car is like something having this length. So it is taking that length. But let's say if you have another image which is giving some more information to the network, so it will be more accurate on it. It will take like 600. Now this seems to be good. Like this doesn't seem to be that well fitting. If you see this, it might be thinking it is something like this. Now this doesn't appear to be a good car. So yeah, and this is looking something good, right? Okay, so that's what I wanted to tell you. If you provide a small image, it won't be a good information for it, but though it will try for having the bounding box accordingly. If you provide a more information to it, it will be more accurate on that. Okay, so this is what we are up to. We have a classifier. Parallelly, we'll be having a bounding box regressor, which will be using L2 loss, and which will be doing both the things parallelly. This will be providing us with the confidence which class this image belongs to, and this arrangement of ours will tell us where the box should be drawn. Let's move further. Let's say we have multiple objects, like we are detecting for person, we are detecting for a board, we are detecting for a TV. Now, how will you decide where the box should be drawn? Of course, you will go through the confidence. You will see what confidence is more. The architecture says it's more confident that board is there with 95% accuracy, right? 95% confidence, it tells that it is a board, and you can take that thing and you can take the coordinates of that and you can just draw the bounding box around it. So you can decide on the confidence. It says there is a person, it detects that here a person is there, here a TV is there, but no need to have those boxes there, right? Why to have those boxes there if the confidence itself is less? Better to decide the threshold on it, that if it goes above 90%, then we'll draw a bounding box around it. So this is some kind of thing, some kind of arrangement that we are doing right now. So I hope you guys are getting it right. Where did we start from? We had a simple classifier. We decided to add some more layers, which will help us out to train a model on x1, y1, x2, y2, and we'll train it using L2 loss, and we'll be having confidence as well as the bounding boxes, and whichever confidence is more, accordingly we'll label it. I mean to say, we'll draw a bounding box around it. Now we have one difficulty. Let's say you have an image of a cat. This is the image of a cat. Now, how do we provide input to a CNN? Now, if you are from the CNN background, if you know about it, we have a fixed size of input for CNNs. You can't input any kind of size. Whenever you define your CNN, the input sizes you have to keep the fixed. If you have to keep it fixed. So if the image is like this, you will manage to do it like this, and you will provide like whatever specific dimension you have decided with CNN. That dimension you will take it, and then you will feed it to CNN. What if I have, let's jump into second scenario. Let's say in a single image you have two different objects. So you might think like, let's divide this image into two and feed it separately, and after whatever outcome we get, we'll stitch this image together. So we might get a bounding box around this cat, and we might get the bounding box around this cat, and then we'll concat them again together, and voila, we got the output, right? But think of it, it can get complicated, right? Let's take example of this thing. Just look at it. We have multiple objects over here, cats to detect, but where should I draw the boundary? Here I said I will draw a boundary in the middle, but how will you provide an intelligence to a software or to an algorithm to detect where should you draw the boundary? Whether should I draw it here, 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 or where should I draw? Is there any particular way that I come to know that where should my boundary be? Because this algorithm, this will detect only one image. What should I do? CNN, what should I do in that? Okay, so neither do I know the number of objects nor the location of the objects. So what can I do? Okay, now comes the scene of sliding windows. So sliding windows were something which were used in the initial era. So what they were used to do is, they used to consider a simple window and they used to slide it across the image. So you can see the sliding window over here, then the sliding window shift towards the right, then it goes till the right portion, then it comes to down, and again it repeats the same procedure till it reaches to the end. I didn't take all the possibilities. Just imagine it. There will be a window which will be going through all the pixels. Now it might find an object here and you will be able to detect it. It might not find object somewhere. That's not of our interest, but somewhere we might be able to get an object, might be here in this window, So eventually when this window will be sliding, it will be taking some objects into it and will be able to get those objects. So you might be thinking now a problem is solved, but think of it, how much computational it will be. You will be sliding the window again and again, and you will be feeding it to CNN networks. Now, CNN network itself, just imagine how many parameters it has and how much computation it will have to do. That's another point. And let's take another point into consideration. Let's say you have an image which is not coming into that window itself. Let's say, just take an example of this man. Now this is your size of a window. Now look at this window, whether it is taking consideration of a whole man, because the man isn't of size of this, right? Let me change the color. You can see the man is something like this much length. Okay, don't go towards that ground truths. Those are ground truth. Yellow color are the ground truth. Just look at this red boxes. Whether this red box will be able to take this whole man into consideration? No, right? It won't be able to take that whole man into single window, and hence our model will not be able to draw a bounding box around it. What you can do is, now comes the famous thing which is known as image pyramid. What you can do is, you have to scale down your image itself. Just scale down your image to some specific sizes. Smaller and smaller the image gets, more and more the image gets into the window. So you can see we have kept the size of the window as constant, and you are able to get a whole man into that picture, a whole man into that window at once, right? And at the end, you might be able to detect the man, and you can get the better detection. So this is what one should be knowing about. Whenever you're gonna read some papers on object detection algorithms, definitely you will be coming across this kind of things as well. So this is the concept of image pyramid. Now you can see that we have scaled the image like 4 times, but there are papers, they have the specific resolution as well, that what size they have reduced it to. So here I've shown 4, but some of the papers, they go for 6 variations as well. And you can see if the object is smaller, that will be coming inside your window, and hence in the first resolution, you might be able to detect a smaller object. And as soon as far like as you go inside of it, like reducing the image dimension and keeping your window constant, you will be able to detect a larger object, just like this man and this bicycle. Okay, so you got the idea of sliding windows. We want to detect multiple objects. We didn't have the idea of where the objects can be, how many the objects can be. Next thing, the hindrance was the scale of the object. It might be a small object or it might be a large object. It might happen that in a single window, both of the things might not come. And that's why you want to go for image pyramid. I hope you got the importance of image pyramid, what they are, and how they can be magical in this kind of algorithms. So we'll make use of this thing as well. So what we'll be doing is, we'll be having one sliding window. And what else we'll be doing is, we'll be taking the sliding window and we'll be going through image pyramid as well. So what have you done? You have taken a window, you will crop out that portion, and you will feed it to your classification object, which will be having a classification and regression of a bounding box as well. But after that, you will scale down your image. You will again scale down your image, and that's how it proceeds. First of all, let's say you have your original image, and you have this sliding window, and this will be sliding through whole image, and it will be detecting the smaller objects. In the first example, I don't think so it will be detecting anything, right? Then again, you reduce the size to a lower dimension. Again, the window size is same. It will be going through whole image. Now it might be able to take out some of the objects which are of the medium size. And again, you scale it down to the third time, and you might get a man over here. I guess you will get a man over here, but you might not get the bicycle, whole bicycle. And again, you will have to scale it down to further. So what is hindrance here? Now, again, the hindrance comes is computation. What are you doing? You are making a sliding window that will crop the things again and again and send it to your network. Your network will be doing classification task. If it doesn't find out any object, the sliding window will slide. In the whole image, it won't find out anything. Then it will go for the reduction of your dimension. Again, the sliding window will perform sliding, cropping of the image, sending it to the classification classifier or net whatever you have, and the classification task will be then again you will not find anything, and this time this thing might go for 6 different variation of your resolution. Now imagine how much computational this thing will be. Feeding, how much images will you feed for a single image for detection? This doesn't sound anything good, right? This much computation for a single image to detect just 2 objects into it, sliding again and again, cropping it again and again, and then again the image pyramid kind of thing. So we have to find out some way out of it. Again, one more problem you can come up with is, let's say you have a sliding window over here. You have a sliding window over here. Okay, here. And it will be sliding over this thing. Okay, at the starting, it will be sliding over this. But tell me, do we have any intelligence over here? Like, do we have any intelligence in the sliding window that where it should be sliding? Just look at this image. This portion doesn't have anything into it. Why should I crop this image? Why should I slide on this image, this portion of image, and send it to the classifier? This is useless, right? Waste of time, waste of computational power. Similarly, if you look here, this portion doesn't have any objects inside of it. So what is this? This is waste, right? Already you have seen that how much computational it can go. You have to crop the image, right? You have to go through all the variation of the resolution of the images. You have to slide through the image. You don't want it. Can't we do something of it? We want to reduce this thing, this useless things. We don't want to go through this portion of images. And now here is where the need came, and something came into picture. Okay, before that, so these are our region of interest, right? We want to detect this thing. This is something which may be something which will be making sense to send to the CNN architecture to detect something out of it. It won't be making any sense to this thing. So I have so red color portion is not of any interest, and green color is something which is of our interest. So we want something which will tell us, like, use your sliding window on this portion only. Use your sliding window on this portion only. You will find something out of it. Don't use it on something like this. This doesn't have any information inside of it. Okay. Okay, so this is what I have written it again. Problem with sliding window technique. It was a brute force method. And again, you have very small images, and those were with the giant counts, right? Huge amount of images you have to take. You have to crop them, you have to slide, and again, you have to go through all the variation of resolution as well. And we don't want to do that. We want to have some smartness, and there are algorithms which came into picture, which smartly tell you that these are the reasons, go for these regions. This will be helpful to tell you that there is something inside of it. There might be something inside of it. Don't go randomly through all the images, all the portion of the images. Don't go through all the images, all the portion of images. Go through the selected areas. Those might be having some interesting objects inside of it, and you can do the classification of it.